I've heard it said that Frederick Dorn could have discovered radon earlier, but he had to wait for Henry Becquerel to discover radioactivity, which he didn't do until 1896. So then Dorn went ahead and discovered radon. 3 naturally occurring isotopes, 219, 220, 222. When people just say radon, normally they're referring to radon 222. The name radon, it was originally called niton, which means from radium. But niton is also said to have been derived from the Roman god Neptune, the god of the sea. And that's what Neptune looks like. So I think it's appropriate that radon be used as a tracer for oceanographic studies. So periodic table of the elements. So radon belongs to group 18 over here, together with helium, neon, argon, krypton, xenon, and here's radium. But what's this? OG, atomic number 118. Well, this is something relatively new. It's a transuranic organocean. It's a synthetic element synthesized in 2002 in Russia. It was actually a joint American-Russian team. You need a cyclotron to make it. It has a half-life of 0.89 milliseconds. So it's probably not going to help us as a SGD tracer, but it is now the heaviest noble gas. It used to be radon was the heaviest noble gas, and it's no longer the case. All right, so a few words about measuring radon. The traditional way of doing it is with what's called a Lucas cell, which is an alpha scintillation cell. And to get the radon into the Lucas cell, you need an extraction line, which is shown on the left-hand side here. So you have a bottle of some appropriate size for the sensitivity that's needed. In the photograph, you can see these large glass bottles. These are 20 liters. And on the order of 20 liters is what people would use for open ocean radon, which is very, very low. If you're doing SGD studies near shore, a few liters, 3, 4 liters, something like that is sufficient. So normally the way this works is you use helium and you sparge the water sample, remove moisture with dry-rite, remove CO2 with ascarite, collect the radon on a cold trap. We use a liquid nitrogen cold trap. Some labs, especially early on, were using charcoal and dry ice, and that works also. And then so the radon condenses on the cold trap. Helium does not, and so it's vented to the atmosphere through this port, which is also used for the quick connect connection to the Lucas scintillation cell. One thing that's really nice about the Lucas cell approach is that the efficiency is very high. From our experience, we normally get a number around 220%. If the world was perfect, you would expect 300%, because for every disintegration of radon, you get 3 alphas. The alpha from radon itself, the alpha from polonium-218, and the alpha particle from polonium-214. You don't, in practice, get a full 300% because there's losses on the extraction line. You can't get 100% of the radon into the Lucas cell. And the Lucas cell itself, because it has to have a window to communicate to the photomultiplier tube, which is used for counting, is not 100% efficient either. So the overall system efficiency, normally we find it a little bit over 200%, which is still very, very good. And so you can measure very, very low levels of radon this way. Who invented the Lucas cell? Henry Lucas. He published this in 1957 and over 60 years ago, and it's still being used quite a bit today. So there's some photos to show you some radon line extractions in progress. This is a former student of mine, Reed Corbett, who's now a full professor and dean at East Carolina University. This is Jay Cable. Interestingly, Jay graduated as an undergraduate from University of South Carolina. And as she was an undergraduate, she worked in the lab of Billy Moore. And then when she graduated, she wanted to get a PhD, but she didn't want to stay in the same institution. So Billy was nice enough to suggest that she come to Florida State, and she did, and did a great job. And she's now, she's a full professor, and she's also an associate dean. And I should mention that Reed Corbett's also a dean at East Carolina. And the other two ladies shown in the photos were volunteers from Earthwatch. And I noticed in putting this together that this lady should really be wearing gloves and a lab coat. So I'm sorry that she's not. So after you manage to transfer the radon to the cold trap, and then from the cold trap to the Lucas cell, you then take the Lucas cell, which this is Christine Rukowski, former student, and she's holding one of the Lucas cells. You can see the white zinc oxide material inside, which is the scintillator. And so you put it in this counter. It's a photomultiplier tube looking up. The Lucas cell is looking down. This is a light shield, and this is all connected to a timer counter to keep track of the time and how many counts are being recorded. Works very well. The only downside is, well, it's a lot of work. The Rad7 that we'll talk about next makes things a lot easier. But it is very sensitive, does work very well. It is quite a bit of hands-on, time-consuming operations. But it is, as we've said, very sensitive. The other down part is that there's no internal tracer. So if you lose any radon during the collection or during the extraction or at any point in the whole system, there's really no way of evaluating that. About the best you can do is to take duplicate samples, which of course would mean that you're going to have twice as much work to do. So sometime in the 1990s, I met this guy, Derek Lane Smith, from a company called Duridge. And Derek said, Bill, you need to use a Rad7 and make your life easier. So we talked about how we might do this. A Rad7 is off-the-shelf radon in air analyzer. It's portable, compact, runs on batteries. If you like, it can also run on line power. Good for field work. Good for lots of kinds of work, including laboratory work. So Derek and I talked about how we could analyze radon in water with a radon in air analyzer. And we thought, what we need is some kind of equilibrator where we could mix water so it equilibrates with the radon in air. So the radon in air is now in equilibrium with the radon in water, and we can derive a solubility coefficient. So if we measure then the radon in air, we can calculate the radon in water. I had a master's degree student working with me at the time, Mike Lambert, and I kind of hand this over to Mike, and he designed the very first Rad Aqua. And if you take a look at this photo, you can probably tell that this is a graduated cylinder. It's a 1 liter graduated cylinder. Mike put a shower head spray nozzle at the top. You can't see it, but it's in there. Used a lot of tubing, as you can see. There's probably some duct tape down in there somewhere. And this was our first Rad Aqua. Eventually, it morphed into what Durage now supplies, which is a nice, neat package. Some of them have one nozzle. This is a nozzle here where you spray, and the spray droplets make it easy for the radon to escape from water into the air. And then you have a closed loop of air circulating through it, an open loop of water going through. You don't actually need to collect any samples. And you can get traces that look like this. This is from our Marine Lab. You can see that this is one of our earliest traces, that the radon activity is highest at the low tide. The water level is very faint here. You may not be able to see it, but you can see the tidal pattern here. And then you can convert that to radon fluxes, which is simply the difference in the inventory, which is, in this case, simply the activity dpm per cubic meter times the water depth, because we're in very shallow water, so we're assuming it's well mixed over time. So you get these radon fluxes. At this point, they're not corrected for atmospheric evasion, mixing with low radon waters offshore, or any other corrections that may be necessary. But this is how you get it started. And even without the corrections, you can make some pretty good estimates of what the groundwater flux is, assuming that the radon inputs into the coastal water is from groundwater. All right, then soon after we had that going, we conceptualized the idea that, why not put several RAD7s together to increase the throughput? So you can still operate with just one exchanger, one open loop of water going through, one drying system. Now, a dry stick is a membrane. It's a Nafion membrane that allows gases like radon to pass, but does not allow moisture to pass. And then that goes to a dry right column. So you don't really need the dry stick, but if you use it, it will preserve the life of the dry right tremendously. So it does help a lot. Then you split the air into, in this case, 3 parts, and then collect it again. And in this case, you would get 3 times as many counts, everything else being equal, than if you just use one RAD7. So you can increase your sensitivity and or decrease the counting time. So this is on board one of our pontoon boats at the Marine Lab. This is Henrietta Dulai, now at the University of Hawaii, and Rick Peterson in the back. He was at Coastal Carolina University in North Carolina, or South Carolina, rather. But he's more recently moved to a Department of Defense, more policy-oriented position in Washington. So we discovered that you could buy these very inexpensive plastic storage boxes the one I'm showing can easily fit 3 Rad-7s for field work. You can put a cover over it to keep the Rad-7s out of the weather, but it's also good for shipping. And with enough bubble wrap and care, we've packaged these things up and pretty much gone around the world with these systems. 2 or 3 boxes like this to include not only the Rad-7s, but submersible pumps and exchangers and drying systems and whatever. One thing you can't easily transport are the batteries, but you can get those anywhere. And so it's not really a problem. All right, so I wanted to say something about sensitivity, and as an example, I'm showing this, this record. This is a week-long record of radon in air in one of our labs at FSU in the old building, actually. So you can see there's a nice diurnal signal here. And by the way, the green is a 3-point smooth and the blue is the raw data. But you get the same, same pattern either way. So virtually all of the data for this week-long experiment is between about 10 and 50 becquerels per cubic meter. If you like DPM per liter better, I converted it for you as 0.63. Very typical numbers. These are not considered high, they're not considered low, they're just, very average. And by the way, if you like the becquerel unit, that is what Henry Becquerel looks like. So what I wanted to do to show you how sensitive these systems can be in measuring radon, if we take these same activity levels, 10 to 50 becquerels per cubic meter, and convert to molar units, we get 10 to the minus 21 to 10 to the minus 20 moles per liter. 10 to the minus 21 molar. I mean, that's incredibly low concentration. Now you can get this from the simple equation activity equals the number of atoms, N, times the decay constant. So we measure the activity, so we have A. We know what the decay constant is. It's the natural log of 2 divided by the half-life. So we can calculate N, the number of atoms. But to go from atoms to moles per liter, we need something else, right? Do you remember? I'm sure you all remember. There was this Italian scientist, Avogadro, and he has a number named after him, 6.02214 times 10 to the 23 per mole. Wow. I bet that 90% of you remember that number. My feeling is that anybody that's had a high school chemistry course will never forget that number because they beat it into us so much, and you have to solve so many problems where Avogadro's number comes into play. I find that very interesting, and we never forget that. But the main point here is that it's really good that radon is radioactive because that's how we measure it. If you had to measure radon with a mass spectrometer, I'm not saying it's impossible, but it would be very, very challenging. And to further illustrate that, this is a slide that I really like to use in teaching because it's a really nice illustration of the relationship between mass and activity. This is from a review paper by Goldstein and all. It was a review paper on uranium disequilibrium dating, if I remember correctly. So what it's showing is a detection limit in femtograms. Now, a femtogram is 10 to the minus 15 grams. So we're talking very, very low here. So it's a detection limit going lower and lower and lower on the y-axis, plotted against nuclide half-life, with the long-lived nuclides on the right and shorter going to the left. So let's compare the detection limit for a multi-collector ICP MS, that's the blue line. So that doesn't change because mass spectrometers measure mass directly, they measure atoms. Let's compare that to alpha spectrometry, which measures activity, not mass. And so this is on a sloping line. So if you're doing uranium, thorium, protactinium dating, you're much better off. In other words, your detection is, your sensitivity is much better, your detection limit is much lower using a mass spectrometer than alpha spectrometry. But notice that right around the half-life of lead-210, actinium-227, which is around 20 years, they're about the same. And then you get into even shorter nuclides like polonium-210, radium-223, and radon, which is not shown here, but I added it. The half-life of radon-222 in years is 1 times 10 to the minus 2. All right, it's 3.82 divided by 365. So we can extrapolate this trend and you get 1 times 10 to the minus 5th femtograms. Femtogram is 10 to the minus 15. So that gives you 1 times 10 to the minus 20. All right, so again, it's good that radon is radioactive, because if it wasn't, you know, we'd never be able to measure it on the way we do now, you know, going out and spending half a day and coming back with dozens of results. All right, so really like that diagram. So some applications. This is literally a textbook example because it's from Wally Broker's 1974 textbook on chemical oceanography. And it illustrates a radon record, a depth profile from the South Atlantic Ocean. And it's showing that in the deeper waters, the radium-226, which is shown by the dashed line, and the radon-222, shown by these circles, are in secular equilibrium. But when you get up to the shallow mixed layer, which is about 40 or 50 meters deep at this station, there's a deficiency in radon. Presumably, what's happened is the radon that would be here has been lost to the atmosphere. So there's been an atmospheric evasive loss. And by knowing what the inventory deficiency is, which would be, so you would integrate the zone that's striped with depth, and by using the well-known equation and assuming steady state, that the flux, in this case, this would be the flux across the air-sea interface, would be equal to the inventory, in this case, the inventory that's deficient in radon, which is the difference between the radium-226 and the radon that was observed, multiplied by the decay constant of radon-222. So a nice way of looking at air-sea gas exchange using radon. All right, but we want to talk about submarine groundwater discharge. So this was an area that for many years was not really paid attention to. There were some real pioneers. Fran Kohout, and I have a expression that a quotation from Mr. Kohout. He worked with the USGS in an office in Miami, Florida. I never had the chance to meet him, but he did some very nice work looking at the interaction of groundwater and ocean water, both shallow and deep on the Florida platform. And he wrote a paper in 1966 and stated that these marvels of the sea, and he was talking about submarine springs, are justifiably classified as neglected phenomena of coastal hydrology. The paper that he wrote in 66 was a review paper on this subject, and he could only find 15 papers that looked at submarine springs from a scientific standpoint. Henry Bokanewicz at Stony Brook was publishing papers around 1980, as early as 1980, and is another pioneer, and there's others. But in the 1990s or so, this started to catch on, and we had some working groups. It was a SCORE working group that myself, Billy Moore, and others were taking part in, and we wrote a review paper in 2003. We defined SGD as the flow of water through continental margins from the seabed to the coastal ocean, regardless of fluid composition or driving force. So we were pointing out that it doesn't have to be fresh water. It can be salt water as well. The driving force doesn't have to be the hydraulic gradient, although it can be, but it can also be forces derived from marine action. 7 years later, Billy Moore wrote another review paper, and he modified this definition by adding the phrase in red with scale lengths of meters to kilometers. And so he was basically saying that what we now call pore water exchange is a different process than submarine groundwater discharge. And I'm fine with that. I think that works. I think it is a different process. Certainly they overlap, and it may be difficult in some cases to actually tell one from the other. And there's some controversy surrounding this, and different people feel different ways. Personally, I would go with the scale length of meters to kilometers. So most of my career has been in Florida, and I moved here in 1977 and didn't know anything about groundwater. But when you start to travel around Florida, you pretty quickly find out that groundwater is a big deal here. 90+% of our domestic water comes out of the Floridan aquifer, which is a huge freshwater aquifer that's not only in Florida, but it extends up into Georgia, South Carolina, Alabama. So it's a huge amount of fresh water. And the springs, of course, are an expression of that aquifer that you can see at the surface. So all of the solid points in this diagram are what they call first magnitude springs, which means they have a discharge of greater than 100 cubic feet per second, which is something like 46 million gallons a day, if I remember right. So Tallahassee is up here. The red dot is Wakulla Springs, which I'll come back to. And the blue dot is Spring Creek Springs, which is actually, it's a submarine spring. There's something like 12 or 13 vents. They all discharge underwater. And collectively, that discharge is the largest spring in Florida, which is saying something. Now, of course, we all know that Florida was discovered by the Spanish, not counting the Seminole Indians that lived here. And they wanted to discover Florida because that's where the Fountain of Youth is located. The legend is that the Fountain of Youth is somewhere around St. Augustine, which is over in that area. I've always found it curious that the Fountain of Youth is in Florida, yet Florida has the highest average age of any state in America. All the retirees come here. Low taxes, good weather. So this is the Wakulla River. The source of the Wakulla River is Wakulla Springs. And the spring looks like this. It's an enormous cavern. It's a whole network of caverns that go down and interact with Spring Creek springs, which are submarine. During the last ice age, these were dry caves, and animals, including Pleistocene mastodons and others that are no longer around, they find fossils in some of these flooded caves. That's Natasha Dimova, who did a lot of nice work on that largest spring, Spring Creek Springs. In fact, this picture was taken there. And it looks like she's giving orders to Jeff Shanton and myself, who seem to be doing most of the work, but Natasha's supervising. So what really got us going on using radon to look at submarine groundwater discharge was some data published by Kent Fannin in 1987. Kent was on the faculty at the University of South Florida in Tampa. I think he's probably retired by now. And this map that you're looking at shows the distribution of near bottom radon 222. And you can see that there's two areas, one that is just offshore of Tampa Bay, right in here, and another one up here that are, they look like they're hotspots. The radon is highest there. Now, Kent, when he published this, he speculated that what we're seeing is being caused by the distribution of phosphate deposits in Florida. Now, there are many phosphate deposits here, mostly in Central Florida, but there are some in North Florida as well. They are enriched in uranium and all of their decay products, including radium and radon. So it's a reasonable, hypothesis. We noticed that in another publication, which is actually earlier, it's published by the State of Florida Geological Survey, that this is showing the distribution of submarine springs, known springs offshore of Florida, and notice that the two groupings seem to correspond to each other. So we propose that the high near bottom radon in these two areas in the Gulf of Mexico were due to groundwater discharge, an expression of these offshore springs. The FSU Marine Lab is just within that northern hot zone, just to a little bit to the west of where the springs are. So let's take a look at a little bit of the data from the FSU Marine Lab, aerial photo on the left. So the diagram on the right showing the water level. It's a mixed semi-diurnal tide. Radon activity this is over a 24-hour mooring. And we also had deployed some seepage meters. The lead type manual seepage meters, which is why there's so few points. The ultrasonic, Peter Swarzinski uses that approach, and the heat pulse or the Taniguchi meter. So at first glance, it appears that the seepage meters shows the highest seepage on the downgoing tide, but the radon activity has the highest radon at the lowest tide. So on first glance, you might come to the conclusion that the radon tracer and the seepage meters do not agree. However, you don't really want to look at the radon concentration per se. What you really want to examine is the radon flux over time. So the flux, again, is the change in the radon inventory over time. So when you do that, the radon flux does agree with the seepage meters, and it looks like the highest seepage is on the downgoing main from the highest high tide to the lowest low tide. And so they do agree, and there's the same equation we looked at easier. The flux is simply the change in the inventory over time, uncorrected in this case for mixing and atmospheric evasion. But it still gives you a pretty good handle on what's going on. So going back to seepage meters for a moment, this is what a Lee-type seepage meter looks like. It's basically a cutoff section of a 55-gallon drum. And this is from one of Jay's papers showing how you use it in a manual sense. You put a plastic bag on the vent. So if you have any seepage through the sand, it'll displace that much water that's in the chamber. It'll come up and be added to the bag. So you do a time deployment, take the bag off, measure the change in volume, and you know the area of the seepage meter, so you get a volumetric flow per unit, area per unit time. It's a direct measurement of seepage. Unlike our geochemical tracers, this is the one way you can directly measure seepage. It was named for David Lee, who wrote the original paper describing how you can make a seepage meter like this. And this is David Lee. We invited him to come down when we first started working on this subject, and he showed us how to best use the seepage meters. And what he's doing here is he's demonstrating how you can make and use what he calls a mini piezometer. So you can actually measure the difference in head relative to sea level. So that's David Lee. We did some very long-term measurements. This is in one of Isaac's papers. So we had a pump set up to draw water in from an intake 300 meters offshore and bring the water directly into our lab, our inside laboratory. We were measuring the water level of the ocean. We had a weather station to measure wind velocity, direction, rain. We measured radon, methane, conductivity, salinity, temperature. From November 2005 to October 2007, almost 2 years, we had over 15,000 measurements of radon 222 in the water from 300 meters offshore of the Marine Lab, all done with a single Rad-7. Not to say that things didn't go wrong over this 2-year period. I don't believe we had trouble with the Rad-7. We had some trouble with the methane sensors, I remember. The pump crapped out at least a couple times. I can remember, and Isaac, you probably remember this too. I remember spending a Christmas Eve. We got a call from people at the Marine Lab that something funny was going on. I don't remember what, but I remember spending the better part of Christmas Eve trying to fix it. I think we did, actually. So that produced some very interesting data. And I thought one of the more interesting things that happened during this period was a storm came by, and tropical storm Alberto, and a lot of interesting things went on here. Let me just focus because I notice I'm running a little late. The storm hit mainly during this period number 3. The wind went up to almost 50 miles per hour. All the rain was during this period. The atmospheric pressure dropped substantially. We had a monitoring well. The level went up by 80 centimeters very, very quickly. After the rain stopped, it only slowly went down, something like 4 or 5 centimeters a day. The radon, shown in red down here, reached its lowest level when the wind was highest, but it responded when the storm passed. The radon responded very quickly, but the salinity did not. You can see the salinity dropped a lot, but it recovered very, very slowly relative to the radon. And that might be because we have this leakage coming from the water table. Some work in Hawaii we did just to show you that in a completely different environment, you can get some similar results. Isaac is taking a look and overseeing what's going on here. So this is from Rick Peterson's work. This is a radon record. This is salinity over 4 or 5 days. Again, the radon is highest when the tide is lowest. So you see the same kind of pattern we see at the Marine Lab in Florida, but this is in Hawaii, where the flow is driven mainly by the hydraulic gradient, modulated by the tides. So some mass balance modeling by Rick Peterson showed that the flow into this Kahalua Bay was something like 3,000 cubic meters per day. Another completely different application, some people that study caves, they look at cave deposits for paleoclimate work and things like that. You can actually work out the ventilation of caves by using radon. So radon in outside air is very, very low, but when the air is stagnant inside a cave, the radon builds up from the radium that's in the limestone, leaking radon into the cave. So you get some very high concentrations during stagnant conditions. And then when these are daily cycles shown on the right, when the air cools outside, then you have this ventilation. When the radon is coming down, means the cave is actually breathing, and then it's stagnant again and it builds up, and then you get this pattern, this day-night pattern. They also see, this is from some of Flip Froelic's work in caves near Tallahassee. I want to say a few words about earthquakes and radon prediction. People have been trying to do this for years. So the idea is that radon enters groundwater via fractures and microfractures. Before an earthquake, stress builds up, either opening or closing microfractures, and anomalies can be either positive or negative. Some people have looked at radon in groundwater, soil gas, and even in the atmosphere. This is a case from Taiwan. It's a hot spring area right there. And in this case, the radon anomalies were negative. In other words, you're getting low points in the radon that preceded a seismic event. So there was 3 events, 6.8, 6.1, and 5.0. And you can see that The tick marks here are about 2 months apart. So the difference, although it looks small on this plot, this is actually the minimum in the radon, is actually a few weeks before the seismic event in each case. So it's actually a quite impressive record. One that's extremely impressive is from the 1995 earthquake in Kobe, Japan. The epicenter is right here along a fault zone. There's an institute here that was measuring radon in over a period of many months. And this is what the radon record looks like. They started in November 93, but then they had a down period, and they started up again in 94. And you can see the radon creeps up. And then 10 days before the earthquake, you got the strong peak, and then it came down again. Then they had a 7.2 earthquake, which was a devastating earthquake. Kobe is right next to Osaka, a very major metropolitan area. Buildings collapse. It's a center of business. It was one of the, not as large as the 2011 earthquake that generated this tsunami in northern Japan, but this was in a much more populated area. Over 6,000 people were killed. It's very devastating. But it looked like radon was trying to tell us something. Another group of Japanese scientists also retrospectively showed that the water chemistry changed leading up to the earthquake. This is showing chloride concentrations. The peak in the chloride actually occurred a few weeks after the epicenter, but there was a trend going up before. Another impressive thing about these two papers, they were published back to back in Science. And take a look at the date, July 7, 1995. The earthquake was January 17th, 1995. So they didn't wait around. They were really on the ball. Another group has been monitoring radon in the atmosphere in Kobe. It was 5 meters over the ground surface. And this is a 4-year record. And you can see that there's an annual cycle where it tends to be highest radon in the summer, lower in the winter. It repeats again. The only time that the radon residual was greater than 3 standard deviations was just before the 1995 earthquake. So that is very impressive. And one thing that I've always wondered is that if you're looking at radon as a predictor of earthquakes, you can't be looking everywhere at the same time. And where you are looking in groundwater probably has a somewhat limited sphere of influence. If you're looking in the atmosphere above an area, you're probably integrating a much larger area. So the chance of picking up a signal, although the activities are going to be lower, you may have a better chance of actually catching something. All right, the final talk. I'm sorry for going over. I didn't realize it was talking so long. The provocative side of radon. So radon is not good for you. The US EPA tells us that. They say that something like 20,000 excess deaths a year in the US are caused by radon. But there are people in the world that think radon is good for you. This is Bad Gastein, which is a spa in Austria. And one reason people go there is to go into these tunnels that have high radon and breathe the radon-enriched air, which they feel has health benefits. This is a Radon Sanatorium in the Ukraine. It treats something like 50,000 patients a year for arthritis, rheumatism, prostate and urinary problems, high blood pressure, infertility, and more. The radon in the bathwater is 25,000 to 35,000 picocuries per liter, which is on the order of 1 million becquerels per cubic meter. Extraordinary. So these are what's called dose effect models. So the one on the left is the linear no threshold model, which is what we use in the US. The one in the middle is a threshold, so you have no effect up to a certain point, and then at that point you start to have bad effects. Another model, which is called hormesis, would say that at low dose, you have a beneficial effect up to a certain threshold, and then the slope changes and you have a negative effect, a negative health effect. This is some data from Bernard Cohen, University of Pittsburgh, that has analyzed indoor radon in tens of thousands of homes around the United States. And what he's done is he's compared the incidence of lung cancer, shown on the y-axis, so that would be the effect, to the activity of radon in picocuries per liter, in this case, and that is the dose. So going back, you expect the slope to look like this, but he's getting a negative slope. So if you take this at face value, you're better off with higher radon in your home than lower radon. You'd have less of a chance of getting lung cancer. Wow, that doesn't seem to make sense. So this is the standard dose effect linear no threshold model. This is what Cohen's data shows. So one possibility is that perhaps this is following the hormesis model, and that Cohen's data is only looking at one part of the data. It's all environmental. And 5 picocuries per liter, which is about the highest he found in all these tens of thousands of homes, is only considered a little high. The EPA action level is 4 picocuries per liter. So if he had more data points at higher levels, he might have seen this change in slope. So who knows? It's interesting to speculate about. But I can imagine that a low dose of ionizing radiation conceivably could have some positive health effects. There are people around the world that have been doing this for years that think so as well. Okay, so to sum up my overly long talk, first of all, I was exceedingly fortunate to have so many great students. I couldn't seem to find the right adjective. I originally wrote incredibly lucky. Maybe that's better. Radon has many applications in the geophysical sciences. More applications are likely to be developed in the future as technology improves, which it always seems to. Radon is considered a health risk, but maybe not always. So I'll end there, and if you have any questions, I'll do my best. Thank you. Okay, right. Isaac, you can take over.
Yeah, thanks so much, Bill. Yeah, so good to see you, and thanks for talking for longer. Usually that's a problem, but it was really nice to to hear you for a bit longer. So I think all of your students in the audience would say the same, that we are so lucky to have found you along our journey. So thanks so much. So I'm gonna open the room, and if anyone wants to start asking questions to Bill, jump in, use the chat, or just unmute and say something.
So, Isaac, this is Jay.
Hello, Jay.
How are you?
Okay,
Hi, Bill. How are you?
I'm
So
doing great.
since we have 90-something participants here, I thought I should just share the first time I ever met Bill. Was at an AGU meeting. I was an undergraduate in Billy's lab, and I saw him give a talk, and I didn't know who he was. I just saw this guy standing in the front of this big auditorium wearing a tweed jacket, as scientists are wont to do. But underneath it was a t-shirt, a white t-shirt, and it just had the radon periodic symbol on it. And he was talking about radon and phosphorites. And at that moment, that was the moment that I knew I had found my advisor for graduate school. So I chased him down in the meeting, and as typical for Bill, I told him who I was, and he said, "Huh, well, apply for graduate school, and I'll let you know." And then he walked away.
Really? Yeah. You know, I don't remember that tweed jacket, but I remember the t-shirt.
Yeah, it was pretty impressive.
Thanks,
So
Jay.
Jay, are you still an associate dean?
Yeah, they haven't fired me yet. I'm waiting.
Oh, I thought you were going to quit.
Well, that is always a possibility too. I'm always teetering on the edge of, am I going to quit or am I going to get fired?
They'd never fire you, Jay. I
Thank
have to
you,
say, I
Jay.
don't actually remember. Yeah, go ahead.
No, you wouldn't have. I was not a known entity in the world. It's all right.
Yeah. Good seeing you,
I
Jay.
have to run. It's great to see you, Bill.
Good to see you. Yeah.
See you,
Thanks
Jay.
for organizing these, Isaac.
My pleasure.
Yeah.
So who wants to jump in and tell us other stories about how you met Bill? I can see Ralph Arnold's cats. Well, maybe I should tell my story about Bill's cats. When I think one of the insights I had about Bill was when I was arriving in the US, and Bill had this old sweater full of cat hair and with the marks of his cat scratching. And then I got home and told my wife, "Oh, I love this guy. You know, I can dress up the way I want." And that has been yeah, another memory of you can just dress up the way you like, right, Bill? Yeah. So does anyone want to jump in and talk about radon? Ralph?
Hey, how's it going? No, hey, how's everything going, Bill?
Oh, doing fine. I'm just tired of staying home,
I understand completely.
like everybody else. Yeah.
I'm sorry we didn't get to China, but